Gemini 3 was the first manned Gemini to be launched. It had been preceded by 2 earlier unmanned test flights. 10 manned test flights would tackle 6 objectives. The program would investigate long-duration flight, develop rendezvous techniques and post-docking maneuvers, develop re-entry flight path control, develop extravehicular capability, attain flight and ground crew proficiency, and conduct scientific experiments. Gemini 3 completed 3 successful orbits on March 23, 1965. It had begun 19 months of manned spaceflight accomplishments. On the very next flight, the long-duration mission headed the list of objectives. Long duration is fundamental to spaceflight. If man could not withstand a zero-G environment for extended periods, 2 things were obvious. Either our future flights would be limited, or gravity would have to be induced artificially in flight. There were 3 long-duration missions, 4 days on Gemini 4, 8 days on Gemini 5, the length of a lunar mission, and an extended mission of 14 days on Gemini 7. Long duration was a test of the endurance of both spacecraft and crew. On the spacecraft side, Gemini 5 was powered by fuel cells for the first time. They replaced conventional batteries. Fuel cells were also flown successfully on all missions from 7 through 12. This is important because batteries are inadequate for many future space missions at the power levels needed. Apollo, for example, will use similar fuel cells. Medical aspects of the flight were closely studied for such everyday matters as the ability to eat and sleep in space, and for longer-term results. When Frank Borman and Jim Lovell completed 14 days in Gemini 7, we had basic answers. We can medically commit crews to flights up to 30 days, a necessary condition for man's role in Apollo and the orbital workshop. The first rendezvous in space occurred December 15, 1965, between 2 spacecraft, Gemini 6A and Gemini 7. Over Hawaii, in the 4th orbit, pilot Stafford reported the decreasing distance between the 2 spacecraft.
120 feet. Holding 120 feet, Wally.
As station keeping continued, Gemini 6A moved within a foot of Gemini 7. It was a successful beginning which saw Gemini complete 10 rendezvous with target vehicles in less than a year. 7 different modes were investigated. An 11th rendezvous to photograph a solar eclipse was achieved on Gemini 12. To those of us who followed the flights from the sidelines, listening to reports from television, rendezvous seemed almost like an automatic exercise. But because something is done well, does not mean that it was easy to do. Rendezvous required 3 years of theoretical preparation, integrating space mathematics into the constraints of the mission and hardware. Approximately 100,000 hours were spent on computer computations. When crews were assigned to specific rendezvous flights, each prime and each backup crew trained for approximately 400 hours in simulators, a total of almost 5,000 man-hours of rendezvous simulation. It was never automatic. Gemini 9A gave us our first sophisticated rendezvous experience. Command Pilot Stafford, a veteran of Gemini 6A, completed 3 different rendezvous within 24 hours with his Angry Alligator. Within 12 orbits, astronaut Stafford completed his initial rendezvous, then performed an optical re-rendezvous using onboard calculations of the pilot as a backup, and finally simulated a type of rendezvous from above the target vehicle which would follow a lunar abort. A dual rendezvous was performed between Gemini 10 and the Agena 8 target vehicle, still in orbit from an earlier launch. It was a passive target vehicle. Gemini 11 achieved an M=1 rendezvous, or rendezvous in the first orbit. This was a direct ascent rendezvous and simulated still another type of rendezvous following a lunar abort. During the first rendezvous, Gemini 6A had moved within 1 foot of Gemini 7, but of course the two spacecraft could not dock. The first space dock came in March 1966. The spacecraft was Gemini 8. Astronaut Armstrong moves in very slowly, making his final approach, until he's about 3 feet from the target. He then holds his position, reading the status display panel on the Agena. When he docks, the Gemini Agena configuration will remain stable for almost 30 minutes. The control problems which developed were unrelated to the first successful dock in space. Gemini completed 9 successful dockings. Both crew members performed dockings on the final 2 missions, 11 and 12. One important aspect of docking is that it allows a crew to utilize the propulsion system of another spacecraft for further maneuvers. The Agena target vehicle has a primary propulsion system with 16,000 pounds of thrust. The primary propulsion system of Agena was first ignited in docked configuration by Command Pilot Young on Gemini 10, and it lifted his spacecraft to a new orbital altitude record of 414 nautical miles. Again on Gemini 11, the primary propulsion system was lit in a white blaze of energy and quickly propelled the crew to 741 nautical miles, shattering the previous record.
Carnarvon 11. Okay, everything's go up here and the world is round. You got a good view? I mean, it's spectacular.
A major post-docking maneuver was the experiment with a 100-foot Dacron line or tether connected to both spacecraft. The command pilot gradually plays out the tether until it becomes taut. On Gemini 11 and again on Gemini 12, we stabilized the spacecraft on the tether without further use of thrusters. 2 techniques were used, the spin-up mode on Gemini 11 and the gravity gradient on Gemini 12. Gemini's demonstration of docking and post-docking techniques, coupled with a long-duration capability, has helped emphasize the continuing utility of manned space missions. Man can assemble vehicles by docking and by tether. He can maneuver them with propulsion burns of spacecraft already in orbit. He can maintain a fixed orientation of space stations without expending maneuvering fuel. In short, we can assemble an orbital workshop and conduct scientific investigations in it for periods up to a month. Controlled re-entry was an objective on all flights. We are looking at the glowing air in the wake of spacecraft re-entry. The command pilot controlled re-entry on the first 8 manned flights. On the final 2 missions, the computer alone automatically controlled the descent. Of course, the pilot was available for backup control. On the first 3 manned flights, Gemini 3 through 5, our landing accuracy was only 57.5 nautical miles from the planned impact point. This distance soon improved. Wally Schirra landed Gemini 6A within 7 nautical miles of the planned impact point. Gemini 8, despite an orbital abort, landed within 1.1 nautical miles of the planned secondary impact point. Although it came down 8,000 miles from the primary target area, it achieved the second-best landing accuracy. Tom Stafford shaved that distance to 0.4 of a mile on Gemini 9A, establishing a remarkable record. Overall, the average miss distance of the last 7 flights was 3.6 nautical miles. This experience will assist us in planning the lunar mission. Crews will be returning from the moon at about 25,000 miles an hour. To land safely within a 3,200-mile footprint, they must hit a re-entry corridor within 2 degrees of the planned flight path. The sheer act of a man opening the Gemini hatch and going into space made extravehicular activity unique among the program objectives. We completed a successful 22-minute spacewalk during Gemini 4. The pilot experienced no disorientation. He maneuvered well with the handheld maneuvering unit, and his physiological reactions were very close to what had been predicted from ground tests. 4 4 additional EVA flights were flown as Gemini progressed from relatively uncomplicated spacewalking to meaningful space work by an EVA pilot. On 3 flights, Gemini 9A, 10, and 11, the pilot faced problems of body control and workload. 2 answers evolved: a new underwater training program for crews, and the increased use of body restraints during work sessions. Astronaut Cernan had 9 pieces of body restraint equipment during his Gemini 9A flight. We progressively developed and refined restraint equipment until 44 pieces were flown on Gemini 12. We also added underwater simulation of zero-G conditions to train the prime and backup crews of Gemini 12. This gave them a greater continuity of training than is possible in the parabola of aircraft flight. Buzz Aldrin put to work the experience gained from 4 flights and underwater training. He completed 19 tasks in a 2-hour, 9-minute EVA. He performed such fundamental space work as activating an experiment, tightening and untightening bolts with an Apollo torque wrench, making electrical connections, and cleaning up his work area. In all, Gemini amassed 12 hours, 22 minutes of EVA experience. It included spacewalking, stand-up EVA for photography, and space work. Gemini EVA has given us assurance that man can work and explore in the vacuum of space, whether that work be on the moon or on orbiting space stations. The Gemini program provided depth in both flight and ground crew proficiency. It trained a staff of flight controllers skilled in handling complex missions. It was therefore quite logical that a Gemini flight director was at the same console for the first Apollo flight. The experience of many other Gemini controllers will also be utilized by Apollo. We came to take for granted the work of the crews at Cape Kennedy, who successfully launched 12 Gemini vehicles. In addition, they demonstrated a dual launch capability. 4 Agena target vehicles and 1 augmented target docking adapter were launched successfully. Recovery personnel of the Department of Defense and NASA reduced the number of recovery ships 50% between Gemini 4 and Gemini 12. At the same time, they increased spacecraft retrieval efficiency by 50%. The record of the flight crews is, of course, better known. When the last spacecraft splashed down, Gemini had logged 1,940 man-hours, almost 40 times as great as Mercury. In cooperation with the scientific community, Gemini flew 52 experiments. Participating were scientists such as Dr. E.P. Nye, director of the Institute of Physics at the University of Minnesota. Over 2,400 synoptic weather and terrain photographs were taken. 2,000 of these supplied useful information to scientists. The aerial mapping potential of manned flights is best illustrated by the Gemini 9A flight over Peru. In one pass, Gemini 9A mapped 80% of the country, and it took just 3 minutes. These photographs were supplied to the Peruvian government. Commercial uses have been many. This Texas coastal area shows the larval distribution of shrimp. One commercial fisherman reported that he learned more by studying this photograph than by fishing the Gulf for 25 years. Weather photographs have been equally rewarding, enabling us to study the vortex of storms and buildup of storm regions in successive photo passes. Gemini has also photographed sources of air pollution over cities, channels of rivers, and the flow of jet streams. The International Affairs Office of NASA makes available such information to interested scientists of all countries. These 52 experiments, the 1,940 man-hours of the 12 Gemini, and the 6 objectives are now over. But the 12 Gemini have given us experience and confidence to tackle the next goals of manned spaceflight. To land for the first time on the moon, explore it, and return to Earth. To acquire new scientific knowledge in orbital workshops, and to reach out toward interplanetary exploration.